Welcome to another episode of Short Takes 331. Today, I want to talk to you about a very important concept called linear independence. And this is how you define this. Suppose you have a vector space and you take n vectors in your vector space. And let's call that set of n vectors a sub n. So the little n here is to encode the fact that we have n vectors. And here are your n vectors. Okay, just n of them, v1, v2, all the way to vn. Now, the question that is really answered by linear independence is this. Is it possible to make this combination a1 v1 plus a2 v2 and so on plus an vn, where the a's are constants, is it possible to make that vanish with non-zero coefficients a sub j? If not, then the set a sub n is linearly independent. If yes, then the set is said to be linearly dependent. So then this is what we have to answer. So suppose we form this combination. Can we make it equal to 0 and not have all these coefficients vanish? So of course we can always set that linear combination. This is what's called linear combination, by the way. We can set that equal to 0 always by taking all the a sub j is equal to 0. The question is whether we can do it without setting all the aj coefficients to 0. If that's possible, then you have a linearly dependent set. If it's not possible, then you're linearly independent. So let's talk more about that using an example. So suppose you're given your two vectors are, suppose you just have two vectors, so n is equal to 2, and the two vectors are v1 and v2 as shown here. So v1 has components 1, 0, v2 has components 0, minus 2, and then we form a linear combination like this. We form this combination a1, v1 plus a2, v2, and so when we calculate that, that gives us a1 times this one, so that goes up here, and then a2 times minus 2, so that goes here, minus 2a2, and then we ask the question, can we set this equal to 0? Yeah, well, yes, we can, but it turns out that the only way to do that is if a1 and a2 are both 0, because to make this number vanish, we have to set a1 to 0, and to make this component vanish, we have to set a2 to 0, so there's no other way, and so the v1, v2 is a linearly independent set, or we simply say that v1 and v2 are linearly independent, or if you want, you can say they're linearly dependent from each other. So at this point, I would like to say that if you like this content, please consider liking the video and subscribing to the channel. It would really help us. This whole channel is meant to help my students in Physics 331 at the University of North Carolina. And if you're not a UNC student, then you can contact me at shorttext331 if you're interested in a math or physics tutor, and we can do that in English or in Spanish, whichever you are interested in. And you can contact me also by leaving a message in the comments section below. So here's another example of a set of vectors that may be linear dependent or linearly independent. So suppose you take v1 and v2 to v1 and 0 for v1 and minus 1, 0 for v2. And we form our linear combination. That's the first thing you should always do, form the linear combination. And then you calculate it and you get a1 times 1 and a2 times minus 1, and you add those together and you get a1 minus a2 comma 0. So can we set this equal to 0? This is what this exclamation mark means. Can we force this to be equal to 0? Yes, we can. We always can do that. We can always set a1 and a2 equal to 0. Then again, the question is, can we do that without forcing a1 and a2 equal to 0? We have to see if that's possible. And so, okay, well, this 0 already took care of itself, this second 0 here. But a1 minus a2 would have to be equal to 0 to satisfy this other part of the equation. And so that means that a1 would have to be equal to a2. And that's all we need. So this means that we're able to satisfy this vanishing of this linear combination without a1 or a2 being necessarily 0. They could be anything as long as they're equal. So any value of a1 will do the job, not just a1 equal to 0. If that were possible, if that were true, that only a1 equal to 0 and only a2 equal to 0, then it would be linearly independent. But in this case, it turns out that we can find a vanishing combination just by setting, for example, a1 to 1, a2 to 1, and we'd be done. So then as long as we set a2 equals to a1, then that will give you a solution to this problem of setting this combination equal to 0, and therefore v1 and v2 are linearly dependent. Okay, we can find a solution that is not just the trivial solution 0, 0. Once again, if the only solution to this problem, setting this equal to 0, is 0, 0 for a1 and a2, then you're linearly independent, you're safe. But if there's more solutions that are non-vanishing, then you would have a linearly dependent set. That's another way to think about it. We can think about this in other examples like functions, which I discussed before, talking about the different kinds of vectors that one might have. functions can be considered vectors. And so here's a function called x, that's a monomial, and here's another one, x squared, is another monomial. They're linearly independent, and the answer is yes. The only way to make this combination vanish identically, yeah, so ax plus bx squared equal to 0, the only way that this would vanish identically for any value of x is that a is equal to b equal to 0. Of course, this also vanishes if x equals 0 in particular, but that's not what we're looking for. We're looking for a solution for which this is exactly the 0 vector. And the 0 vector in the space where x and x squared live, it's just a function that is completely 0 everywhere. And there's no way to accomplish that other than with this solution, a equals b equals 0. And that's the only solution you have that satisfies this equation for all values of x. And so the set of x and x squared as vectors is linearly independent. So this is another way of saying you cannot transform x into x squared by multiplying by some constant or by forming some combination where you just multiply by a number or add a number times another function. So the only way is to multiply by x. Yeah, and so but we only are talking about x and x squared here. The only way to make that vanish is if a and b are 0. So what does this mean, this concept of linear independence in general? Well, geometrically, two vectors are linearly independent when they're not collinear. So this is a case of two vectors. So in fact, the examples we saw above are cases of just two vectors, and they are linearly independent if they're not collinear. So this means that they really point in different directions. That's sort of the general concept, that they sort of point in different directions. Two vectors that are lying on the same line, like in this other example here, v1 and v2, can be cancelled against each other. So you can form a linear combination of these two and set it equal to 0, and you can find that they can be cancelled out in many ways. On the other hand, the only way to form 0 out of these two vectors is if you multiply both of them by 0. There's no way to cancel them out in any other way. So this is what happens for two vectors. Now for three vectors, linear independence means that they're not all on the same plane. So if you have three vectors and they're all on the same plane, then you can find a way to cancel them out one against the other. On the other hand, if one of them is sticking out like this, then you're safe. Then these two down here on the plane are linearly independent. Of course, they're not on the same line. And this one here is sticking out, so there's no way you can cancel these guys out against each other by forming some linear combination, unless that linear combination is just a trivial one where all the constants are 0. Algebraically, there's another way of thinking about this. Linear independence means that it is not possible to write one of the vectors a linear combination of the others. Okay, so suppose that we have this linear combination set equal to 0. This is our search for linear dependence or independence. And suppose that we find out that this is possible to do, and with A3, say, one of them, not equal to 0. Okay, so we find that it's linearly dependent because there's a solution where one of them is not equal to 0. Then we can put all the terms on the other side of the equation except v3, a3, and then we divide by a3, which is allowed because a3 is non-zero, and then we've managed to write v3 in terms of all the other vectors. Okay, so and this is possible to do because the set is linearly dependent, and so there's one of them that is non-zero. So if the set were linearly independent, we would not be allowed to do this. It would simply not be possible, because if this is equal to 0, then the only combination is where all the a's are 0 and you cannot divide by any of them. And so you cannot write one of them in terms of the other. So that's another way to look at linear independence. In the case of two vectors, going back to that example, linear dependence means basically that one of them is proportional to the other. And you can show that it's very easy. If a1 v1 plus a2 v2 equal to 0 has a solution where one of the constants is non-zero, basically both constants will be non-zero, and you can write one vector in terms of the other by putting it on the other side of the equation. That's very easy to see. It's also very easy to see that any set containing the 0 vector is linearly dependent, because we can always have a constant times that 0 vector equal to 0 for any constant a, not just a constant equal to 0. And so any set that includes the 0 as an element of it, so if one of our v1, v2, vn is just a 0 vector, then that set will be automatically linearly dependent. So if you want to form a linearly independent set, which is desirable as we'll see in the future, then that 0 needs to be removed and replaced with something else, or simply removed. So more generally, I want to say more formally that this object we call here, this expression, is what we call a linear combination of our vectors v sub I, and sometimes we will write it in a more compact form in this way. as a sum using the big sigma notation from j equals 1 to n. As you see here, it goes up to n. It starts at 1 of some coefficient a sub j, v sub j. So typically when we say a linear combination of these vectors or a linear combination of this or that, this is what we mean. We mean a sum of constants times these objects that we may be talking about. In this case, of course, it's vectors. Sometimes people informally talk about a linear combination of an idea with another idea when they say it's something in between. And so sometimes physicists do that. And that's all I have for you today. I hope you find this content useful. If so, please consider liking and subscribing to the channel. And like I said, this is meant for my students at the University of North Carolina. If you're not a UNC student, but you're interested in finding a tutor for physics or for math, then I can probably help you in English or in Spanish, whichever you prefer. And you can find me at shorttakes331@gmail.com, or you can leave a comment in the comment section below and reach out to me that way. That's all I have for you, and I hope you enjoyed this video. Until next time.